Okay, now you can start.
Okay, thank you. Firstly, I apologize for yesterday because I couldn't present and attend the conference because I have teaching of a course at this time. So my presentation will deal with about the thermodynamic properties of the different chemical oscillator in a uniform magnetic field with the extended uncertainty principle. I am a recruited teacher in the University of El Wed in Algeria, and these are my supervisor and the co-supervisor Mustafa Moumni and Mukhtar Farq from Khanshla and Batna universities in Algeria. So this work will deal about the solution of the different Kemer-Patio scalar case and vector case oscillator in a uniform magnetic field in the deformed space of the anti-de Sitter space. Then we are going to deal with the thermodynamic properties with the partition fraction Z. So this is just a brief introduction here.
Can I stop you 1 second? Can you go to presentation mode on your PowerPoint?
Okay. That's work.
No.
Okay, because
Go to. I think it's on the bottom.
I am in the introduction slide.
Yeah, but you're not in presentation mode.
Okay, I mean in the presentation mode. You can't see it?
I can see it, but it's not in presentation mode. I want to see the entire screen, the entire slide.
In my PC, it's the presentation mode, but in yours, I don't know.
You probably have to switch screen that you're sharing. That's probably the issue.
I will just a second.
Yeah, let's try that.
This is like this. Right now, you can see the introduction.
No, it's still not in presentation mode. Well, okay. Why don't you just keep going, and we'll
okay
make amends.
So in this brief introduction, I'm giving some information about the gravity in the quantum world and the generation of the great interests of the all authors in the quantum field theory, which deal with the curved space through the generalization of the Heisenberg algebra, such as the extended uncertainty principle. And the goal of this principle is to take in account the fluctuations. من تحت عملت بريزنتاسيون برك كونفيرونس عندي كونفيرونس برك من تحت هم في قاعة الدكتوراه اوكي this extended uncertainty principle, its goal is about the count of the quantum fluctuations of the gravitational field in order to include gravity in the quantum mechanics domain. And one of the consequences of the standardization of the existence of minimal length scale of the Planck order. And our equation will be the Diffie-Mercatio equation, which is some complex dynamic of the spin 0 and spin 1 boson combined and described by the first order equation with the Dirac-like properties. In addition, it has been a very intricate algebraic structure. Furthermore, its solution were thought to be equivalent to the Klein-Gordon and the Broca equation in the shell cases prior to 1919. So right now you can see these equations or not?
I cannot. You have to go to the next slide. Okay. There you go. That's better.
So these are some relations in the deformed space are given in the Heisenberg algebra leading to the first extended uncertainty principle in the anti-de Sitter space in this following equation there. And the Lk is the angular momentum variable expressed as follow in the second and third equation there. The modified Heisenberg uncertainty is given in the fourth equation here, as we can see the delta x and the delta pi. So if we assume the isotropic uncertainties given just like this form, we can get the minimal uncertainty in the momentum by the fifth equation. So we can also define the usual position and momentum operator with which has satisfied the empty de Sitter algebra, where the x, the big one for the position and momentum, are the deformed one, and the small one here, the x, and normally here the derivation of the pi of the momentum in the usual position and momentum. So right now we are going to when we find the position and momentum, we are going to involve these expressions in the equation of the DKP. So the DKP equation, we can write it in the two-dimensional deformed stationary equation for the stationary solution here, where we have transformed the momentum and the position by this following equation here, and the B is the intensity of the magnetic field as we can obtain it. The psi here, normally we have two cases we are going to deal with. For the scalar case, normally the wave function of the P0 have 5 components, so that we are after solve these 5 components and obtain the equation. We can obtain this by solving this system. We can obtain this simple differential equation here. This this equation, it's the same as the Klein-Gordon equation, and by obtaining the polar coordinates and by using the Nikiforov-Uvarov method, I can obtain the energy eigenvalues of this system by this following form here. And the ninth equation, as we remarked, this expression is dealt with the deformation of the space. As we can see, it's corrected. There are some corrective terms dependent on the deformation of the space of the parameter lambda. For example, here when we put the lambda goes to 0, we can obtain the energy spectrum of the Diffie-Hellman-Pareto equation in the usual case. Also, we obtained the wave function of this system by using the Jacobi polynomial equation series in order to obtain this following form of the wave function. As we can see, there are five components of the psi here, as we can watch in this slide here. So after this equation, or after this case, we are going to go to the vector case, where with the wave function of the system has 10 components. And this complex form, we are not going to solve directly, because it's impossible to get the exact solution. So we are going to use the non-relativistic limit of the system. So after calculated the scalar term and the vector term, as we can see there, we can obtain this following equation here, where the psi here is the non-relativistic limit of the system, and by using it, we can obtain this equation there. Also here, there are a lot of observation and a lot of results we can obtain it from. Firstly, the system has corrective terms dependent on the deformations parameter of the lambda here. Also, we can remark that there are the spin orbit coupling with the deformation and the ordinary spin orbit of the system. So moving on to the thermodynamic properties, where we have obtained the partition function Z, and by simplify it by using Euler-Maclaurin series, Taylor series, a lot of mathematical calculation. We can obtain the partition function by this following form. Then we can plot the free energy, the mean energy, the specific heat, and the entropy using their deformation, as we can remark it here. So by plotting it by Mathematica software, we can obtain these graphs here for the figure 1, figure 2, figure 3, and the figure 4, where the first figure is the free energy according to the temperature for various value of the deformation parameter. The blue one here shows the ordinary case, where here for the green and the red one is of the deformed, and we can remark that there is an effect of the deformation on these graphs of the all the properties, thermodynamic properties of these clues or these results. Moreover, we can are obtained from, where we have studied that
Hello? You still with us? Hello?
There is an interrupt
Yep,
in my
we can
internet
restart
also.
where you left off. Okay.
Hello?
Yes, restart where you left off.
Hello?
Yes, we can hear you.
Okay, this is just a conclusion of this presentation here. Can you hear me or not?
Yes, I can hear you.
Okay, so these are some main results that we have obtained. So that I will tell you just about the exact results that we have obtained. So our results show that the deformed spectrum remains discrete even for a large value of the principal quantum number, and which removes the degeneracy of the spectrum found in the ordinary case. Moreover, in this case of the vector case, since it is almost impossible to find the exact solution, so we have obtained, we have used the non-relativistic limit of the case, and we have obtained the usual spin orbit term of the new spin orbit, which represents the interaction of the spin with the orbital momentum and the space deformation at the same time. Finally, we have used the partition friction in order to get the thermodynamic properties of the system in the graphical representation. Also, we have showed that the results agree with those found in the graphene in Schneider de Sitter curved space, and this difference is more pronounced for the free energy, which increases in the deformed case while it decreases in the ordinary case. Also for the entropy, which has a relation between the free energy and the entropy of this thermodynamic properties. And thank you for your attention, and thank you for your patience. Any questions if there are?
I don't know if the other participants have any questions.
Okay.
But I'm just reading through this last slide.
Okay.
Is there a triplet repulsion term, like a spin repulsion term in the Hamiltonian that you? I didn't see that in the first equations.
In the first equation here, sorry, here for
Yeah,
The Hamiltonian of the DKP equation.
right. Where's like the exchange type term?
Normally, the Hamiltonian of this equation here is defined by the momentum, as we can remark it here in the in the deformed space. We can see this root normally is according to the deformation of the space. We can, if we put, for example, lambda goes to 0, we can obtain just the pi. Here we can obtain just the r, so that our equation will be pi p minus r, for example, minus e imw of this new for the r, just all this expression of the Hamiltonian.
Okay.
Okay, because here we have used the oscillator expression, as we can see the im omega, and here the interaction of the magnetic field for the intensity of the magnetic field B. That's all.
Got it. Okay.
Okay.
Now, how could this theoretical development be validated experimentally?
Actually, this is a theoretical study, so that normally it's in the high energy area, so that we cannot use it in the reality. Or I have another study that I have made of the graphene. Here in Algeria there is not a lot of tools in order to get the experiment. Maybe in Germany or in this Switzerland, there are tools that they told me, if you are able to do your experiment in their labs. But I have graduated, and there is no time to do these experiments.
Okay,
Okay, that's all.
understood.
Okay.
All right. Well, thank you very much for your presentation.
Thank you for your team. Thank you for your time too. And I am sorry for your delay. Okay.
No problem.
Thank you so much. And
All right, you're welcome.
see you on the next event, inshallah. That's
All right,
all.
cheers.
Thank you. Seriously.
All right.
Goodbye.